Next, we are going to see some basic definition concepts regarding evolution of contour integration, because we are going to use this contour integration to solve Fourier transformation problems. So that is why. So just we go through that. Jordan's lemma. If the integrating a complex function f of z into e power I a z along a semicircular arc in the upper half plane or lower half plane, if a is negative, right, if a is positive, it is on the upper half. If a is negative, it is on the lower half. And if modulus f of z is bounded on this arc, so arc means a semicircular, so right, part, then the integral over the semicircular arc will tends to 0 as the radius of the arc goes to infinite. So this is the Jordan lemma. And next one causes integral formula. If f of z is analytic with in and on a simple closed contour C, right, and z0 is the point inside C, then f of z0 which is equal to 1 by 2 pi I integral over the contour f of z by z minus z0 dz. Next cause is residues theorem. If f of z is analytic inside and on C, a simple closed contour except for a finite number of isolated singularity within C, then the integral of the function f of z around C is equal to 2 pi I times the sum of the residues of f of z inside C. That is integral over the contour f of z dz is equal to 2 pi I into sum of the residues of f of z inside C. Next, pole of a function f of z is a point in the complex plane at which the value of the given function f of z becomes infinite. So for example, if you take f of z is equal to sin z by z into z minus 2 into z minus 5, so z equal to 0. So for at that point the function is infinite, because in the denominator if you are getting 0, the function will be infinite. So z equal to 0, next point z is equal to 2, z is equal to 5 are the poles of f of z. If the poles having the power, then it is called degree or order. Suppose if you are having z square in the denominator, then z is equal to 0 is the pole of order 2, like that. Suppose if you are having sin z by z minus 2 the whole square or whole cube or whole power 5, then z is equal to 2 is a pole of order 2, 3 or 5, like that. So this is a simple pole, order is 1. So how to find the pole? So to find the pole, just equate the denominator of the given function f of z to 0 and solve for z. To find the value of z, just right, then you will get the pole. Now residue of f of z at pole z is equal to z0 of order 1, single pole formula. Just we are using this only. So this is enough for this our part. That is what I am taking this one, order 1, single pole formula. Residue of f of z is equal to z0, which is equal to limit z tends to z0, z minus z0 into f of z. Above the real line means upper half of the plane based on e power ia z, right? E power ia z rotates counterclockwise for a is greater than 0. Suppose if you are having e power minus ia z counterclockwise, if a is a negative into negative, positive you will get, right? So a is negative. So below the real line or lower half, e power ia z rotates clockwise, that is a less than 0, right? E power minus e rotates clockwise if a is greater than 0, right? To evaluate the integral, we will have to choose the contour first. The usual procedure is to define the closed contour such that one segment of the loop is real line. So it is on the real line, minus infinite to plus infinite, straight line, like. Then you have to take the route of the semicircular path, and the other segment of the loop is turn around, right, and return the complex plane to the close the loop. This is this is called closed contour or closing the contour, right. We choose the close the contour to close the contour along the anticlockwise semicircular arc in the upper half of the complex plane. So like this. So the arrow mark indicates the direction. So pole is inside the contour, upper half. Normally we will choose y-axis as the imaginary axis, real axis as the x-axis. So minus infinite to plus infinite real axis, then it will go to the semicircular path. This is downwards based on e power I a z, right, below the real line, right. Thanks.